In December of 2022, a team of astrophysicists at the Space Telescope Science Institute in Baltimore sat down to examine the first deep-field images returned by the James Webb Space Telescope. They had been preparing for this moment for years, decades in some cases. These were not excitable graduate students encountering space imagery for the first time. These were seasoned researchers, people who had spent entire careers working with Hubble data, people who understood intellectually, mathematically, precisely what Webb was capable of seeing. They were not prepared for what they saw. One researcher, who has since declined to be named in press coverage of the moment, reportedly left the room, not to celebrate, not to call a colleague. She left because she needed a moment alone. When she returned, she said 4 words to the team before the debrief began: "I don't feel real." That reaction, from a professional scientist with 30 years of observational experience, tells you something that no press release and no official NASA statement has fully captured. It tells you that what James Webb is showing us is not simply better data. It is not simply higher resolution imagery of things we already knew existed. It is a confrontation, a forced encounter with a reality so vast, so ancient, so structurally alien to the scale at which human beings are designed to think, that the mind, even a trained, disciplined, mathematically sophisticated mind, recoils from it. The universe is not what we thought it was. If space fascinates you, a like and subscribe means everything to us. Let's begin. Here is what you need to understand about how we see the universe, because it changes everything that follows. When you look at a star, you're not seeing the star. You're seeing light that left the star. Light that has been travelling through space at 299,792 kilometers per second for a duration of time that depends entirely on how far away that star happens to be. The nearest star to our Sun, Proxima Centauri, is 4.24 light-years away. The light you see from it tonight left its surface 4 years and 3 months ago. The star you're seeing is a 4-year-old image, preserved in photons, delivered to your eye across an almost incomprehensible distance. That's the nearest star. Now scale up. The Andromeda Galaxy, the nearest major galaxy to our own Milky Way, visible to the naked eye on a clear dark night as a faint smudge in the constellation of that name, is 2.537 million light-years away. The light arriving at your eye from Andromeda tonight departed that galaxy when our species' ancestors were not yet fully human, when the creatures who would eventually become Homo sapiens were just beginning to use stone tools in East Africa. That light was already on its way. It has been travelling for 2.537 million years, and it is only now arriving. You're not looking at Andromeda. You're looking at a 2.537 million-year-old photograph of Andromeda. This is the nature of cosmic observation. Every telescope, every instrument humanity has ever pointed at the sky, is a time machine, and the more powerful the telescope, the further back in time it can see. Hubble, at the peak of its capabilities, could detect light from galaxies approximately 13.4 billion light-years away. Galaxies that existed when the universe was only about 400 million years old. Infant galaxies, newly formed from the chaos of the Big Bang's aftermath. Webb can see further. Not a little further, not incrementally further. Webb's primary mirror, 6.5 meters in diameter, composed of 18 hexagonal gold-coated beryllium segments, collects approximately 7 times more light than Hubble. It operates primarily in the infrared spectrum, which allows it to see through the dust clouds that blocked Hubble's vision and to detect the extremely redshifted light of the most distant objects in the observable universe. Light that has been stretched by the expansion of space itself during the billions of years it took to reach us, stretched from visible wavelengths into infrared wavelengths that Hubble was never designed to detect. What Webb can see in its deepest exposures is light that has been travelling for approximately 13.6 billion years. The universe itself is estimated to be 13.8 billion years old. Webb is looking at galaxies that formed within the first 200 million years of cosmic history. The universe was barely a toddler when the light we are receiving now first left those ancient, distant shores. But here's what nobody fully prepared us for. It's not just that Webb can see further back in time, it's what it found when it got there. The history of observational astronomy is, in a sense, a history of progressive humiliation. Each time humanity has built a more powerful instrument and turned it toward the sky, the universe has revealed itself to be larger, older, more complex, and more indifferent than we had previously assumed. And each time, we have required a period of adjustment, a collective recalibration of our place in the cosmic order, before we could incorporate the new reality into our understanding of ourselves. The first great humiliation came in the early 20th century. For most of human history, the Milky Way was the universe. The stars we could see, the band of light crossing the night sky, that was everything. When astronomers began detecting faint fuzzy objects called nebulae and debating what they were, the dominant view was that they were clouds of gas within our own galaxy. The idea that they might be entire galaxies in their own right, island universes, each containing billions of stars, separated from us by distances so vast they made the Milky Way itself seem small, was considered fringe speculation. In 1924, Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory to resolve individual stars in the Andromeda Nebula. He identified a specific type of star, a Cepheid variable, whose pulsation rate is directly related to its luminosity, and used it to calculate the distance to Andromeda. His answer: approximately 900,000 light-years. Later measurements refined this to 2.537 million light-years. Either way, the conclusion was unavoidable. Andromeda was not a cloud within our galaxy. It was an entirely separate galaxy, itself containing hundreds of billions of stars. The Milky Way was not the universe. It was one galaxy among many. How many? At the time Hubble made his discovery, astronomers estimated perhaps a few thousand galaxies in the observable universe. As telescope technology improved, that number rose. By the time the Hubble Space Telescope was launched in 1990, estimates had reached into the hundreds of millions. Then, in 1995, the Hubble team pointed their new instrument at a tiny, apparently empty patch of sky in the constellation Ursa Major, a patch so small it subtended an angle of 2.5 arc-minutes, about 1/30th the diameter of the full moon, and left the shutter open for 10 consecutive days. The result was the Hubble Deep Field, and what it revealed in that tiny sliver of apparently empty sky was approximately 3,000 galaxies. Not stars, galaxies. Each one containing billions to hundreds of billions of stars, in a patch of sky so small you could cover it with the tip of a grain of sand held at arm's length. Scale that up to the entire sky. Do the mathematics. The answer that emerged from the Hubble Deep Field was that the observable universe contains approximately 200 billion galaxies. 200 billion entire galaxies. The number was so large that it had almost no cognitive purchase. You could repeat it, you could write it out in numerals, but you could not feel it in the way that you feel the scale of a mountain or an ocean. 200 billion galaxies. That was the universe we thought we lived in. Then, Webb turned on, and revised that number upward by a factor of 10. Let's be precise about this, because the precision matters. In 2016, a team led by Christopher Consulis at the University of Nottingham published a paper in the Astrophysical Journal that used Hubble data combined with mathematical modelling to estimate the total number of galaxies in the observable universe. Their conclusion: approximately 2 trillion galaxies, 2,000 billion, 10 times more than the previous estimate of 200 billion. The revision was based on the recognition that Hubble was not powerful enough to see the smallest, faintest galaxies in the early universe, that for every galaxy Hubble detected there were roughly 9 others too dim, too distant, too small to register. Webb, in its first year of science operations, began confirming what those models had predicted, and then it went further, because Webb didn't just see more galaxies, or it saw galaxies that had no business being there. This is the part of the story that has the scientific community in a state of sustained, controlled alarm. Not the kind of alarm that makes headlines easily, not a discovery of alien life or a planet on a collision course with Earth. A quieter, more fundamental alarm, the alarm of a model breaking. The standard model of cosmology, the Lambda CDM model, which describes the composition, evolution, and large-scale structure of the universe, makes specific predictions about what the early universe should look like. It predicts that in the first few 100 million years after the Big Bang, matter should have been relatively smoothly distributed. Galaxies should have been small, primordial, embryonic collections of gas and young stars, gradually building up mass and complexity over billions of years through mergers and accretion. Webb pointed at the early universe and found something different. It found large, massive, remarkably well-developed galaxies existing at redshifts, distances, that the standard model said should be occupied only by infant structures. Galaxies that appeared to contain stellar populations billions of years older than they had any right to be, given when in cosmic history they existed. Galaxies that were, in the language of the researchers who discovered them, impossibly massive. That word, impossibly, appeared in peer-reviewed literature, in careful, measured scientific papers published in prestigious journals, describing objects whose existence contradicts the predictions of our best cosmological model. Not anomalies that fall slightly outside the probability distribution. Objects that, according to the model, simply should not be there. How many? In Webb's first deep field images alone, researchers identified 6 candidate galaxies at extremely high redshift. Galaxies from the universe's first 700 million years, whose stellar masses were estimated to be between 10 billion and 100 billion times the mass of our Sun. One candidate, designated CEERS-1749 in the Cosmic Evolution Early Release Science Survey, appeared to have a stellar mass approaching the mass of the Milky Way, and existed when the universe was only 500 million years old. In the standard model, a galaxy of that mass should not have had time to form. There was not enough time. That is not a casual statement. It is a statement about physics. Now here's where it gets truly strange. To understand why massive early galaxies are so destabilizing, you need to understand how galaxies form, or rather, how we thought they formed. The standard picture of galaxy formation begins with dark matter. Dark matter, the invisible gravity-producing substance that makes up approximately 27% of the universe's total energy content, but emits no light and interacts with ordinary matter only through gravity, is the scaffolding on which the visible universe is built. In the immediate aftermath of the Big Bang, quantum fluctuations in the density of dark matter seeded tiny variations in its distribution. Regions that were very slightly denser than their surroundings exerted slightly more gravitational pull. They attracted more matter. They grew over hundreds of millions of years. These overdensities, called dark matter halos, grew large enough to begin capturing ordinary matter, hydrogen and helium gas, the raw ingredients of stars. As gas fell into the gravitational wells of dark matter halos, it compressed. It heated. In regions dense and cool enough, it fragmented into clumps that collapsed under their own gravity and ignited, becoming stars. The first stars in the universe were almost certainly enormous by current standards, perhaps 100 to 1,000 times the mass of our Sun, burning briefly and ferociously before exploding as supernovae, seeding the surrounding gas with the first heavy elements and triggering new rounds of star formation. This process, gas infall, star formation, stellar evolution, supernova feedback, more star formation, takes time. The models predict that building a galaxy with a stellar mass of tens of billions of solar masses requires several billion years of accumulation and merging. The universe is estimated to be 13.8 billion years old. A galaxy at redshift 10, which corresponds to a time when the universe was only about 500 million years old, simply has not had the time to accumulate that mass under the standard model's predictions. And yet, Webb sees them. There are several possible explanations, and the scientific community is actively debating all of them. The first and most conservative is that our estimates of these galaxies' stellar masses are wrong. Mass estimates for distant galaxies depend on models of stellar populations, assumptions about the mix of stellar types, ages, and luminosities that produce a given observed brightness. If those models are wrong, if early galaxies were brighter per unit mass than we assume, then the actual masses might be lower than the estimates suggest, and the discrepancy with standard cosmology might be less severe than it currently appears. Researchers are working on this. It is not resolved. The second explanation is more unsettling. Perhaps the standard model of galaxy formation is incomplete. Perhaps there is a mechanism, or several mechanisms, by which mass can accumulate into galaxies faster than the current models predict. Perhaps dark matter behaves differently in the early universe than in the late universe, Perhaps the rate of star formation in early galaxies was dramatically higher than anything we have observed in local galaxies. Perhaps the physics of the primordial universe, at energies and densities that no laboratory on Earth can reproduce, permitted a mode of galaxy assembly that we have not yet incorporated into our theoretical framework. The third explanation is the one that nobody wants to say out loud in polite scientific company, but that several prominent cosmologists have begun to discuss in print. Perhaps the Big Bang itself, the foundational event of our cosmological model, the moment from which we date the universe's age of 13.8 billion years, is not the complete picture. Perhaps the universe is older than we think. Perhaps the expansion history of the universe is more complex than lambda CDM describes. Perhaps, and this is the edge of the scientific imagination, and the place where mathematics and philosophy begin to merge, our observable universe is not all that there is. Sit with that for a moment. The observable universe is a sphere approximately 93 billion light-years in diameter. Not the age of the universe times the speed of light. That calculation gives you 13.8 billion light-years in each direction. The observable universe is larger than that because space itself has been expanding during the time that light has been travelling. The light we're receiving from the most distant objects was emitted when those objects were much closer to us than they are now. In the time that light has been in transit, the expansion of the universe has carried those objects to distances far beyond where they were when the light left. The result is an observable universe of 93 billion light-years, the region within which light has had time to reach us since the Big Bang. Beyond that sphere, there is more universe. How much more? We do not know. The region beyond our observable horizon is by definition causally disconnected from us. No information, no light, no signal of any kind has had time to travel from there to here. We cannot observe it. We cannot measure it. We cannot, in any empirical sense, know what it contains, but we can reason about it. The current best measurements of the universe's geometry, derived from the cosmic microwave background, the faint afterglow of the Big Bang that permeates all of space, suggest that the universe is spatially flat, or very close to flat at the largest scales we can measure. And flat in cosmological terms means that the geometry of space follows Euclidean rules. Parallel lines never meet. The angles of a triangle sum to exactly 180 degrees, rather than the curved geometry of a sphere or a saddle. If the universe is truly flat and infinite, then it extends forever in all directions beyond our observable horizon. An infinite universe containing an infinite amount of matter and energy, an infinite number of galaxies, stars, planets, an infinite number of everything. Infinity is not a large number. It is not a number at all. It is a concept that our brains, shaped by evolution to navigate a world of finite distances and finite quantities, are fundamentally ill-equipped to process. You can write the symbol, you can manipulate it mathematically, you cannot feel it. No human being can. And yet, if current cosmological measurements are correct, that is the universe we inhabit. Not just large, not just very large, not just incomprehensibly large, infinite, without edge, without boundary, without a beyond in any meaningful spatial sense. Webb is not showing us the edge of this universe. Webb is showing us the edge of what we can see, and what it is showing us at that edge is already breaking the models we built to explain it. Here is where the terror becomes personal. Because the scale problem, the problem of galaxies too massive too early, is not the only anomaly that Webb has delivered in its first years of operation. It is the most dramatic. But it is accompanied by a series of other findings that, taken together, paint a picture of a universe that is more structured, more complex, and more alien in its early history than any of our models predicted. Webb has detected galaxies at redshifts corresponding to the universe's first 300 million years that show evidence of chemical enrichment, the presence of heavy elements like carbon, oxygen and silicon that can only be produced in the cores of massive stars and distributed through supernova explosions. For those heavy elements to exist in detectable quantities at such early cosmic times, entire generations of massive stars must have been born, lived and died before the universe was 300 million years old. Entire stellar generations, in 300 million years. The standard model struggles to accommodate the pace. Webb has detected evidence of supermassive black holes with masses millions to billions of times that of our Sun, at redshifts corresponding to the universe's first 700 million years. supermassive black holes, in the standard picture, grow through the accretion of matter over long timescales. Finding them already enormous in the infant universe is, like the massive early galaxies, a problem of time. There is not enough of it, not in the standard model, to grow a black hole to 1 billion solar masses in 700 million years, starting from the stellar mass black holes that form as supernovae remnants. And Webb has observed large-scale structures, filaments, sheets, and voids in the distribution of galaxies that appear to be more developed, more organised, those more spatially extensive than the standard model predicts for those early epochs. The cosmic web, the large-scale structure of the universe, the vast network of galaxy filaments and clusters separated by enormous voids, appears to have assembled more rapidly than theory anticipated. Each of these findings, individually, could be an anomaly, an edge case, an observational artifact that a more careful analysis will explain away. But together they form a pattern, and patterns in science demand explanation. Dr. Alison Kirkpatrick, an astronomer at the University of Kansas, who was among the first researchers to analyse Webb's early galaxy data, described her reaction in an interview that has since been widely cited. She said she experienced what she described as an existential crisis when she first examined the data. Not a personal crisis, a scientific one. She said, "And I want to be careful to represent this accurately because the language matters. We have these large, massive galaxies early in the universe that we just don't expect to exist, and I feel like right now I'm just struggling to explain. A senior astronomer, an existential crisis, because the data doesn't fit. That is where we are. But that's not the full story, not even close. Because the scale of the universe, the sheer geometric enormity of it, is only one dimension of what Webb is revealing. The other dimension is time, and when you combine the spatial scale of the universe with its temporal depth, something happens to the human mind that is qualitatively different from any other encounter with large numbers. You realize that everything, every civilization, every species, every planet, every star, every galaxy in the observable universe is not just spatially remote from everything else, it is also temporally isolated, separated not just by distance, but by the irreversible flow of time across scales so vast that the history of our entire species, from the first stone tool to the last satellite, occupies a period that is cosmologically invisible, less than a rounding error, a single frame in a film billions of frames long. The light Webb collects from a galaxy 13 billion light-years away left that galaxy 13 billion years ago. That galaxy, or rather, the matter that once composed it, has had 13 billion years to evolve since that light departed. In 13 billion years, stars have been born and died by the billions within it. Planets have formed, perhaps supported life, perhaps lost that life, perhaps supported it again. Civilizations, if civilizations arise with any regularity in the universe, could have risen, flourished, built instruments far beyond our comprehension, and gone extinct multiple times over in the time that their light has been travelling toward us. We're not seeing those galaxies as they are. We are seeing echoes, fossils of light, carrying information about a state of affairs that has not existed for longer than the Earth has existed. The universe we can observe is, in a profound and literal sense, a museum. Every object in it is a historical artifact. The further you look, the deeper into history you go. And at the deepest depth that Webb can probe, the first few 100 million years of cosmic time, you are looking at a universe so different from the one we currently inhabit that calling them both by the same name feels almost misleading. That universe, the universe Webb is showing us in its deepest exposures, was hotter by orders of magnitude. The cosmic microwave background, the afterglow of recombination when the universe first became transparent to light, had not yet cooled to the 2.7 Kelvin it occupies today. It was hundreds of degrees warmer. The first atoms, hydrogen and helium, the simplest elements, had only recently formed from the plasma of the Big Bang's immediate aftermath. The first stars were just igniting, enormous and short-lived, burning furiously in a universe that had never before known starlight. No planets. Then no heavy elements, no complex chemistry, no possibility yet of anything we would recognize as life. A universe in its absolute infancy, raw and ferocious, undergoing a transformation whose end result, 13.8 billion years later, includes planets and people and telescopes and the people who build them. Webb is showing us the beginning of that transformation, and it is showing us that the transformation was already more complex, more structured, more rapid than we had any right to expect. Now here's where it gets truly strange, because there is a discovery woven through Webb's early science that is simultaneously the most technically subtle and the most philosophically destabilizing of everything the telescope has returned so far. It concerns the expansion of the universe, specifically the rate of that expansion. In 1929, Edwin Hubble, the same astronomer who established the extragalactic nature of the Andromeda Nebula, published observations showing that distant galaxies are moving away from us, and not just moving away randomly, they are receding at velocities proportional to their distances. The further away a galaxy is, the faster it appears to be receding. This relationship, now called the Hubble-Lemaitre law, is the observational foundation of Big Bang cosmology. It tells us that the universe is expanding, and if the universe is expanding, then in the past it was smaller, denser, hotter, and if you extrapolate backward far enough, you arrive at the Big Bang itself. The rate of cosmic expansion is characterized by a number called the Hubble constant, denoted h0. It measures how fast galaxies are receding per unit of distance, in units of kilometers per second per megaparsec, where a megaparsec is approximately 3.26 million light-years. Getting the right value for the Hubble constant is fundamental. It sets the age, size, and expansion history of the entire observable universe. For decades, measuring the Hubble constant was one of the great observational challenges in astronomy. The uncertainty was enormous. Different methods gave substantially different answers. The launch of Hubble was partly motivated by the need to resolve this uncertainty. And Hubble delivered. Using Cepheid variable stars as distance markers, the same technique Hubble the astronomer had used to establish Andromeda's distance, the telescope eventually pinned the local Hubble constant at approximately 73 kilometers per second per megaparsec. Meanwhile, a completely independent measurement of the Hubble constant became possible using the cosmic microwave background, the afterglow of the Big Bang itself. The ESA's Planck satellite, which produced the most precise maps of the cosmic microwave background ever obtained, derived a Hubble constant of approximately 67 kilometers per second per megaparsec. 67 versus 73. Those numbers sound close. They are not close. They are separated by a discrepancy, a tension, in the carefully restrained language of cosmology, that has persisted for over a decade and that multiple independent measurement techniques have failed to resolve. Every time a new method is devised to measure the local expansion rate independently, it comes up closer to 73. Every time the measurement is derived from early universe physics, it comes up closer to 67. This is the Hubble tension. And Webb is making it worse, because Webb has now been used to independently calibrate the Cepheid distance scale, to check whether there are systematic errors in the measurements that Hubble the telescope used to establish the local value of the Hubble constant. The Webb observations found no significant systematic errors. The Cepheid distances are solid. The local Hubble constant, as measured by direct astronomical observation, appears to be genuinely, robustly around 73, and the early universe value, derived from the cosmic microwave background, is genuinely around 67. Those two numbers describe the same universe at different epochs. In a universe described by the standard cosmological model, they should be the same. They are not. And the discrepancy, now measured at a statistical significance of approximately 5 sigma, meaning it has less than a 1 in 3 million probability of being a random fluctuation, is not going away. What does it mean? The most conservative interpretation is that there are still unidentified systematic errors in one or both measurement methods, subtle biases that are artificially pulling the numbers apart. This is possible. Scientists are human. Measurement systems have flaws. History is full of apparently significant discrepancies that turned out to be calibration errors. But the discrepancy has survived every attempt to find those errors, and it has survived long enough and been confirmed by enough independent methods that a growing number of cosmologists are beginning to seriously consider the alternative. The alternative is that the standard model of cosmology is wrong. Not wrong in a minor correctable way. Wrong in a way that requires a fundamental revision of how we understand the universe's evolution. Wrong in a way that might require new physics. Physics beyond the standard model. physics that has not yet been discovered, physics that might change our understanding of what the universe is made of, how it began, and what it will ultimately become. The implications of this are almost too vast to comprehend. Let's be specific about what new physics could mean in this context, because the possibilities range from the relatively mundane to the genuinely reality-dissolving. One class of explanations involves dark energy. Dark energy, the mysterious component of the universe responsible for its accelerating expansion, currently accounts for approximately 68% of the universe's total energy content. We do not know what dark energy is. We describe it mathematically as a cosmological constant, a fixed energy density of empty space, uniform throughout the universe and constant in time. But this description is purely phenomenological. We're naming something without understanding it. If dark energy is not actually constant, if it varies in space or time in ways that our current observations have not detected, then the universe's expansion history could be more complex than lambda CDM describes, and the Hubble tension could be a symptom of that complexity. Recent data from the Dark Energy Spectroscopic Instrument, a survey instrument at Kitt Peak National Observatory in Arizona that has measured the positions and velocities of tens of millions of galaxies, suggested in 2024 that dark energy may not be constant. The data hinted that dark energy might be weakening over cosmic time, that the energy density of empty space may have been higher in the past than it is today. If confirmed, and this would be the first evidence that the cosmological constant is not constant, the first crack in the most fundamental assumption of modern cosmology. Webb's observations of the distant universe are providing additional data points that will help constrain these models, but they're also complicating them. Because a dynamic dark energy that varies in time would affect not just the expansion rate of the universe, but the formation of large-scale structure, the rate at which dark matter halos form, the rate at which galaxies assemble, the timing of the cosmic web's development. And those predictions can be tested against what Webb is observing in the early universe. Preliminary comparisons are not entirely reassuring. The universe Webb is seeing appears, in multiple respects, to be more organized at early times than even an adjusted dark energy model would predict. Which brings us to the edge of the scientific imagination, the place where the data points if you follow it without flinching. Some cosmologists have begun to take seriously the possibility that the universe had a history before the Big Bang. This sounds like a philosophical speculation. It is increasingly a serious scientific hypothesis supported by mathematical frameworks with testable predictions. Several competing models have been developed. The conformal cyclic cosmology, proposed by mathematical physicist Sir Roger Penrose, in which the universe undergoes an infinite series of expansions, each aeon ending in a state geometrically equivalent to the Big Bang of the next. The bouncing universe models, and in which the Big Bang was not the universe's first moment, but a transition from a prior contracting phase, a cosmic bounce, driven by quantum gravity effects that prevented the contraction from reaching a true singularity. Eternal inflation, in which the Big Bang was a local event within a larger, eternally inflating background space, a bubble of expanded space-time embedded in a vast quantum foam from which other bubbles, other universes, are perpetually nucleating. These are not fringe proposals. They are published in peer-reviewed journals, developed by physicists at major research institutions, and taken seriously by a significant fraction of the cosmological community. They are not accepted consensus, but they are not dismissed as pseudoscience. What they share is a common implication. The universe we inhabit, the 93 billion light-year sphere of observable space and time that Webb is probing, may not be the entirety of existence. It may be a region, a patch, a bubble. One instantiation among many of something larger, older, and more complex than any model we have yet constructed. And here is the detail that should make you pause. If any of these pre-Big Bang cosmologies are correct, if the universe has a history before the Big Bang, or if our universe is one among many, then the massive early galaxies that Webb is finding might make sense, not as violations of our model, but as evidence that the universe's initial conditions were not the smooth, nearly uniform state that standard inflation predicts. If the universe had a more complex prior history, or if it is embedded in a larger structure that influenced its initial conditions, then some regions might have been denser, more structured, better seeded for rapid galaxy formation than the standard model assumes. The early massive galaxies might not be anomalies, they might be clues about a history so vast and so ancient that the 13.8 billion years we currently assign to the universe is merely the most recent chapter of a story with no discernible beginning. Let's hold that thought and return to the human scale, because there is a dimension of Webb's revelations that the technical discussion can obscure, a dimension that is not about physics or cosmology, but about what it means to be the kind of creature that can ask these questions at all. Carl Sagan wrote in the 1980s that we are a way for the cosmos to know itself. That observation has become something of a cliché, repeated so often that its content has worn thin. But stand with it for a moment in the context of what Webb is showing us and see if it still feels true. The universe is, by the most conservative estimates, 93 billion light-years across in its observable extent, and potentially infinite beyond that horizon. It has existed for 13.8 billion years, possibly far longer if pre-Big Bang cosmologies are correct. It contains at least 2 trillion galaxies, each containing hundreds of billions of stars, each star potentially accompanied by planets, each planet potentially harbouring conditions that chemistry could exploit. Against that backdrop, one small rocky planet orbiting an unremarkable star in the outer spiral arm of one average galaxy among 2 trillion, which after 4.5 billion years of chemical and biological evolution produced creatures capable of building a mirror 6.5 meters across, cooling it to negative 233 degrees Celsius, launching it to the second Lagrange point 1.5 million kilometers from Earth, and using it to see light that has been travelling for 13.6 billion years, and then sitting down together to argue about what it means. There is something in that image that resists the terror, not because the scale isn't overwhelming, it is, not because the questions aren't unresolved, they are, but because the act of asking the question, the very capacity to be humbled by the scale of the answer, is itself the most remarkable thing in the observable universe. We know of no other place in 93 billion light-years of space where matter has organised itself in such a way as to look at the rest of matter and ask, how large is this? How old is this? Why does this exist? We might not be alone in that. Probably we are not. But we know of no one else doing it. And that isolation, that cosmic loneliness, that sense of being a consciousness adrift in an ocean of incomprehensible scale, is not just terrifying. It is, if you hold it at the right angle, extraordinary. There's a photograph. It's called Webb's First Deep Field. Released publicly by NASA on July 11, 2022, the first full-colour scientific image from the James Webb Space Telescope. In it, a field of galaxies is visible, thousands of them, distorted into arcs and rings by the gravitational lensing of a galaxy cluster in the foreground, a cluster called SMACS 0723. Behind that cluster, a distance is so vast that the light has been travelling for billions of years, galaxy after galaxy after galaxy fills every corner of the frame. The field of view covered by that image is approximately the angular size of a grain of sand held at arm's length. One grain of sand, held at arm's length, thousands of galaxies. Scale that to the entire sky, scale that to the universe, try to hold that number, 2 trillion galaxies, and feel what the researcher felt when she looked at the first Webb data and left the room. I don't feel real. She felt that because the mind, confronted with a reality that completely exceeds its capacity for comprehension, does something strange. It doesn't simply fail to understand. It understands that it's failing. It becomes aware of its own inadequacy. And in that moment of awareness, that moment of standing at the edge of what cognition can process, and looking out at what lies beyond, something changes. You cannot unsee 2 trillion galaxies. You cannot unknow that the light in that image has been travelling for billions of years, while the planet you stand on cooled, and oceans formed, and life began, and complex organisms evolved, and your species built language and civilization and science. And finally, a telescope sensitive enough to catch those ancient photons and turn them into an image a human eye can see. You cannot unknow that the universe does not know you exist, that it has no care for your survival, no interest in your questions, he has no investment in your answers, that it will continue expanding, accelerating in fact, driven by the dark energy we cannot explain, long after every star has burned out and every black hole has evaporated, and the last quantum of organised matter has dissolved into a cold, dark, structureless void that will persist for timescales so enormous they cannot be written in standard notation. That is what the universe is doing. That is what it has always been doing. And yet, here, in this brief, improbable window of cosmic time, something in it is asking why. What happens next will reshape everything. Webb's mission is designed to last at least 10 years. It launched with sufficient fuel for a 20-year mission. In the time remaining to it, it will continue probing the early universe, continue challenging the standard model, continue delivering data that the theoretical community will spend decades incorporating into revised frameworks. The anomalous early galaxies will be studied in greater detail. Their spectra will be analysed for chemical composition. Their morphologies will be mapped in 3 dimensions. The Hubble tension will either deepen or resolve. The nature of dark energy will either remain mysterious or yield its first genuine clues. And ground-based facilities are coming online that will work in concert with Webb to push the boundaries further. The extremely large telescope, currently under construction in the Atacama Desert in Chile, will have a primary mirror 39 meters in diameter, nearly 6 times the diameter of Webb's mirror, capable of obtaining spectra of individual stars in distant galaxies, capable of directly imaging exoplanet atmospheres, capable of probing the universe at resolutions that make current instruments look primitive. The Square Kilometre Array, a network of radio telescopes distributed across South Africa and Australia, will map the large-scale structure of the universe across cosmic time with a precision that no existing instrument can approach. We're not at the end of this story. We're at the beginning of the chapter in which we first begin to understand how much we don't know. That is the position Webb has put us in. Not triumphant certainty, but productive uncertainty. Not answers, but better questions. The kind of questions that, when you follow them honestly and rigorously, lead to a revised picture of reality that is always larger, stranger, and more magnificent than the one it replaces. The universe is not what we thought it was. We knew it was large. We did not know how large. We knew it was old. We did not know how complex its early history was. We knew it was expanding. We did not know that the rate of that expansion is in tension with itself in ways that our best model cannot resolve. We knew it contained galaxies by the hundreds of billions. We now know it contains them by the trillions, and that the galaxies at its farthest visible reaches are defying our models of how galaxies should form. We know that beyond the farthest thing Webb can see, there is more. How much more? We cannot say. Possibly infinite more. Possibly more universes in structures and configurations that the physics we know cannot describe. And in all of that incomprehensible, model-breaking, reality-dissolving vastness, we are here. We built the mirror, we launched it, we pointed it at the dark, and the dark looked back. One thread remains unresolved. One question that Webb has not answered, that perhaps no instrument ever can answer, that lives at the boundary between physics and philosophy and refuses to be confined to either side. If the universe contains 2 trillion galaxies, and if even a small fraction of those galaxies contain stars with planets, and if even a small fraction of those planets developed chemistry complex enough to produce life, and if even a small fraction of that life developed into something capable of looking up at the sky and wondering, then the universe is full of minds, full of questions, full of instruments pointed at the dark, and none of them, as far as we can tell, can hear each other. Why? The universe is 13.8 billion years old. The distances are vast, but not in principle unbridgeable over geological timescales. If intelligence arises with any frequency at all in a universe of 2 trillion galaxies, the silence should not be this complete. And yet it is. The sky's quiet. The radio spectrum is empty of anything that looks like intention. Webb has found no signatures of technology in the atmospheres of distant planets, though it has barely begun to look. The Fermi paradox, that great unsettling silence, remains as paradoxical as ever. Webb will not solve the Fermi paradox, but it will, in its remaining years of operation, push the boundary of where we look and what we look for. It will characterize the atmospheres of Earth-sized planets in the habitable zones of nearby stars, searching for the chemical signatures, oxygen, methane, water vapor, that might indicate biology. It will look at the early universe and try to determine whether the conditions for life's chemistry, were as widespread then as they are now. It will help us understand whether we are typical or exceptional in a universe of 2 trillion chances. That answer, typical or exceptional, changes everything. Not just about the search for life, but about what our existence means. About why, in a universe that does not know we exist, we feel compelled to understand it anyway. The universe is not what we thought it was. Neither, perhaps, are we.